Hello, everybody. These notes are about linear regression, also called least squares regression lines, and the related concept of residuals in R squared. And I know you probably know some stuff about this already. There might be some new things. Follow along and enjoy. So this is real data from the 2016-2017 NBA season, where there are 13 players, and the total minutes in the entire season they played, along with the total number of points in the entire season they scored. And as you might expect, there is a positive linear, well, not necessarily, you wouldn't expect it to be linear, but there's a positive relationship here. You'd expect that the more minutes you play, the more points you score. If you were going to describe this, think to last week. What would be a good tight sentence that would describe this? I would say the relationship between minutes played and points scored is a relatively strong, positive, linear relationship. So rather than use math, I just used my eyeballs to draw this line in Desmos, and then this was the equation, 0.38 minutes plus 0.25, and there's a problem here having to do with the meaning of hat. So the meaning of hat, you remember from last week, is a predicted value. So I'm not predicting a number of minutes and then using that to predict a number of points. Let's remove this hat. So minutes is my explanatory variable, and then points is my response variable, because it's responding to how many minutes. So cool. So this equation is my linear model. Let's interpret the slope. So this 0.38, what would you say that means? And this is, again, like 1 point in an FRQ problem. You see this a lot. So you might be tempted to say something like there are 0.38 points for points scored for each minute played. But that's missing a really key word that is on the scoring rubrics, and that word is predicted. So players are predicted to score 0.38 points for each minute played, or maybe for each additional minute played. The reason why predicted is if we don't have that, you are literally claiming what's going to happen in reality exactly. You are saying that players are definitely going to score this much for each minute played. And that's not what you want to say. It's not what you intend to say. You intend to say that your model predicts how many points are going to get scored on average for each additional minute played. All right, so in a second, we'll think about how could I improve this linear model. I said I just determined it with my eyeballs. Like, what's a better way of figuring out a model that has less error, that makes more accurate predictions? But if we're going to talk about more accurate predictions, we have to talk about residuals. Residuals are the errors for individual predictions of the model, and they're calculated as the actual value minus the predicted value. So let's go ahead and circle these two data points. This 809 is here, 863 is there, and the table they're here and here. So go ahead and fill in actual predicted, and you can calculate this on the calculator using the equation, and then the residual, and then I'll tell you about the meaning. And pause the video. So there's my actual points. In case it's not obvious how to do predicted, I will type it in now. So here's my equation up here at the top. So for minutes, I'll have like 809 minutes, and then I'll multiply it by 0.38, and then I'll add 2.5, and so for predicted, I have 309.92. Okay, this is the most important part. There will definitely be multiple choice questions about the meaning of positive and negative in a residual and being able to identify them in a graph. So here is the 809 point right there. This is the residual, that distance between here and here. For the 863 point, this is the residual, is this distance. Let's think for a second about this actual minus predicted. So actual would be this height here, and predicted would be that height there. So you can see why this one ended up being negative. It's because the actual height is smaller than the predicted height. One way of thinking about the word residual means like what's left over. So if you think about what's left over after I make my prediction, what's left over is this kind of negative amount that gets me to my actual. Whereas in this case, I make my prediction, and what's left over after my prediction to get me to the real value is this positive amount, because it's above the line. If that helps you, use that. If that doesn't help you, forget I ever said it. But you do need some way of making sense for yourself of what the meaning of the positive and the negative residuals are. So just again, as a self-test, a negative residual means that the true value is, or let's put it this way. For a negative residual, was my prediction an over prediction or an under prediction? For a positive residual, was my prediction an over prediction or an under prediction? So the meaning here is that I predicted 88.92 points too large, above the real value. Whereas here, I predicted 189.56 points below the true value. So again, be ready to interpret the meaning of the positive or the negative sign on the residual. All right, moving right along. So what would the best linear model be? It makes sort of intuitive sense that the best model should be the one with the most accurate overall predictions on the data that we have. So how are we going to measure the accuracy of the predictions over all of the data? That's one question. And another question is, what can we change about our model to possibly increase its accuracy? So there's two things that we can change about a linear model. We can change the slope, or we can change the y-intercept. In general, those are called the parameters of the model. Later on, we'll have other kinds of models that will also have parameters, but you can think of a parameter as sort of a number that describes the overall shape of your model in some way, or that describes some characteristic of your model, and it's a number that you can change. So like imagine having sliders in Desmos, like anything where you can slide the slider and your overall model will change somehow, you can think about that as being a parameter of the model. Okay, so our task of finding the best fit line is we need to figure out what values of the parameters, what slope and y-intercept, will give us the smallest overall error. This is not the only way to calculate error, but for linear regression, we calculate it using something called the Sum of Squared Residuals, or it's often abbreviated RSS for residual sum of squares. And here's how it's calculated. Let's remember what all these bits mean. So the sigma here, that big E looking thing, means add up all the following. And then this y with a subscript I, usually you imagine your data as being in a table like this. And you sort of imagine numbering the rows. So I1 might be the first row, and I2 might be the second row, and I3 might be the third row. So when we have a subscript I here, what we're imagining is we're imagining the sigma saying I is going from 1 up to whatever the number of rows in our data set is. And so this is just like a math shorthand for saying, let's visit every single row and let's take the actual y value in our row and subtract the predicted y value for our row. So really this subtraction is just the same thing as residual. Y subscript I is the actual value for row I. Y hat subscript I is the predicted value for row I. So if you want to, you could say add up all of the actual minus predicted values squared. Why are we squaring them? The reason we're squaring them is because, as you remember, one of these is positive and one of them is negative. So if we add them together, we don't want them to cancel each other out to tell us, oh, we have overall 0 error, if actually we have perfectly balanced errors between over-predicting and under-predicting. So put differently, we want the magnitude of the error. We don't care about the direction. So instead of taking the absolute value, we'll square it, which would take a negative number and make it positive. Another effect of squaring it is it means that small values don't increase by as much as large values. So here's what I mean. Let's look at a small residual. So here's a relatively small residual. If I'm going to imagine squaring it, you could literally imagine a square and the area of that square. So if the absolute value of the residual is this height, and then I take that height and I make it the same as the width to form a square, then the residual squared is the area of that little square. So you can see that a small residual has resulted in a small square. A large residual is going to result in a much larger square. And so you could imagine all of these squared residuals, just kind of sketch these in. So what RSS is referring to is it's referring to adding up all these areas. And that's our measure of how accurate is our line. And you could imagine if I moved the line even further away from the points, the residuals are going to get larger and the squares are going to get larger. And when I add them all together, it will be more overall area. Okay, let's find the best fit line using our calculator. So the best fit line, again, is the line that will give us the smallest residual sum of squares. So start out by going to Stats, Edit, and enter all the data in list 1 and list 2 for the number of minutes and the number of points. So this should be list 1, this should be list 2. Double check when you're finished that the lists are the same length. If I go down to the bottom, see how the lists are the exact same length? If they're not the same length and you try and find the best fit line, there will be a syntax error. Okay, so how do you find the best fit line? Go ahead and pause the video, enter the data if you haven't already. So for the best fit line, we'll go to Stats, over to Calc, and then down to LinReg, which stands for Linear Regression. There's this one, which is AX plus B. You could also do this one, which is A plus BX. The only difference is the order that it tells you the slope and the y-intercept. Whatever you want to do is fine. So I'm going to do this number 4. I'm going to use list 1 as my x values, also called the explanatory variable. Here's the y values, list 2, that's the response variable. So I'll just go all the way down to calculate. And so here it's telling me y equals ax plus b, and it gives me the value for a as the slope, and it gives me the value for b as the y-intercept, and also r and r squared. So here, let's write this down and then talk about what it means. Ta-da! No, of course not. We would never just write y and x like this in a stats class. Let's try again. There we are, much better. So get in the habit of using the names of your variables. Use a hat for a predicted value. Okay, so it's giving you r and r squared. R you know about already. It's confusing that it gives you r here because r actually has nothing to do with your model. The value for r you can know before you have any line at all, because r is just about the relationship between two different variables in your data. It has nothing to do with the line. R squared is going to be about your model, and that's what we're going to talk about right now on the back page. Okay, so r squared tells you how much of the variation in your data can be explained by the explanatory variable. And what I mean by how much is the percent of the total variation. So this is confusing for students, but I think it's just because we've always explained it wrong. So let me try and explain it in a way that hopefully will make sense. Here's some data that shows the test scores of 20 different students on a 100-point test, and here's all the scores. And if we just list the scores, you can see that there's quite a lot of variation in the test scores. This is the mean right here. The mean test score is 73.55, and it's got a standard deviation of 11.03. So here's like +1 standard deviation, and here's -1 standard deviation. So you can see there's all of this variability around the average score. And that's what we want to explain. We want to say, why is it that some students scored above the average and other students scored below the average? It might be that it's just totally unpredictable and it's completely random. Like there is no other information that would let us predict who's scoring higher and who's scoring lower. For this particular case, that seems unlikely. So you can probably think, why don't you like brainstorm right now 3 or 4 things that you think might be related to test scores that would let you predict if they could score higher or lower than the average. So maybe you're thinking things like their prior course preparation. Like what did they, like how strong did they come into the course? Maybe you're thinking, how much did they study for this particular test? Maybe you're thinking, like some people have like better memories than others. So maybe it has to do with like how good your memory is. Maybe it has something to do with something else. So those are all possible explanatory variables for this thing that we want to explain, which is the response variable. So let's imagine some data here. Whoa, ooh, let's try and think about like these three lowest scores for a second. So this is let's call this student A, and this student B, and this student C. Okay. So A is, where are they in the data? All right. So go ahead, circle those three scores, and let's label those students A, B, and C. So here I have a whole bunch of other information that's not shown in a table, so you can't actually see the numerical values. But what this is this is the test score. Go ahead and fill that in. So this is the test score plotted against their prior grade. Like maybe their grade in last year's math course, or maybe their grade in the course up till now. And as you can see, students with higher prior grades tend to have scored better on this test. So there's a positive relationship there. But it doesn't perfectly predict their score. There's some students who had a high prior grade but scored lower than we might expect, some who scored higher than we might expect. So this doesn't explain all of the variation in the test scores. Let's look at this model. So here it's the same response variable, the score on this test. Here it's the number of minutes studied. And again, there's this positive relationship. In general, students who studied more minutes are scoring higher on the test. But again, it's not explaining all of the variability. Like this student looks like they scored way below what we would have predicted just based on minutes studied. So all of this is to say, there are lots of ways usually to explain variability in data. And when you're coming up with your models, you're trying to find the variables that can explain the most variation. And that's one-dimensional linear regression. You can also do something called multiple regression, because you might think, well, wait, isn't it better to predict the score based on two different things rather than just based on one thing? And you are right. Multiple regression is something that we're not going to talk about in this course, but you can ask if you wonder about, because it's actually not so hard. Okay, so go ahead and try and fill in this data table based on like visual estimates. So for students A, B, and C, we know what their real score was. Student A scored 51, student B scored 57, student C scored 58. Go ahead and try and fill in based on these two graphs, like how much time did they spend studying? What was their prior grade? All right, so I've listed the R values for these two scatter plots. And again, R has nothing to do with this line. R is just about the strength of that relationship between the two variables. Let's calculate R squared. So there's a really, really important thing to know, which is that, I guess let's write it here. So R squared is equal to little r squared only for a least squares regression model. So what that means is both these equations were found using the calculator or using the computer to minimize the overall residual sum of squares. So if that's the way that we found the equation, to find big R squared, you just square little r. That would not be true if you go back to the front page. Where's my front page? So here, if I found the R for this data set and I squared it, that would not tell me the R squared of this model, because this model I didn't use any math for, I just used my eyeballs. So R squared only has this special relationship to R for LSR models. So go ahead and calculate the R squared now for both of these, and then we'll interpret them. All right, so there we go. I've just squared each of the R's to get the R squareds. What does it mean to say that this model has an R squared of 0.545? It's telling us the percent of the variability in our response variable that can be explained by the explanatory variable. So let's write a good sentence. We'd say 54.5% of the variation in score, because that's the response variable, can be explained by their prior math grade, which was my explanatory variable for that particular plot. Here's what that doesn't mean. Look at the picture here. Is it true that 54% of my data go through that line? Definitely not. the data is all over the place. So we're not explaining how much of the data is perfectly predicted by the model. We're trying to explain the variability. So we're trying to explain all of these distances from the mean value that we saw originally. And so it's not about how many data points, it's about how much of all of those added up differences, it's about how much of all of those added up distances can be explained by this other variable. So that's what we mean when we say how much of the variability or how much of the variation can be explained. You'll see over here that the number of minutes studied, only 30% of the variability can be explained by that. So for this particular test and this particular group of students, it looks like their prior math grade was a better predictor than the number of minutes they studied. All right, let's bring it on home. So this box is how you actually calculate r squared by hand if you want to. And this is sort of true in general. So RSS is the residual sum of squares from the first page. That's this thing. TSS is called the total sum of squares. And it's what you get if you add up all of the squared differences between each of your observations and the mean value. And it represents the total variability. So here, let's annotate this a bit. Okay, so on the bottom here, we have the total variability in scores. Up here, we have the variability that's left over after we make our prediction based on our model. So a good way of thinking about this is I am taking the difference between each observation and the mean value. So up here, here's the mean value in the middle. The difference between each observation and the mean value would be all of these distances squared. So that's all the variability adding up, if I added it all up. On the top, these are, again, residuals. So it's all the variability that's left over after our prediction. So here we've got a prediction, but notice all the data points aren't right on the line. So the amount that our points are above or below the line is additional variability that our model can't predict. If all the data points were perfectly on our line, that would mean that we're predicting all of our data perfectly, and there is no additional variability left over after our predictions. So you can think about this ratio as being sort of like as like a percentage, and that, again, sort of like if you want to think it out, like why should it make sense that 1 minus that percentage ends up telling us the percent of variation that can be explained by the explanatory variable. All right, what else did I want to tell you? Okay, go ahead and sketch, based on what I just said, go ahead and sketch some sample data in a line where RSS would equal 0. Like, what does it look like if there is no variability left over after our prediction line? And so we'll look at those in class. Finally, let's go ahead and make a summary table here. So R is also called the coefficient of correlation. Sometimes the word Pearson is attached to it. And it tells you the strength of the correlation between variables. Maybe we should write the word strength. So strength of correlation between variables. This doesn't have anything to do with the model. Okay, and it's between -1 and +1, and hopefully you remember -1 would mean some kind of perfect inverse relationship, and +1 would be some type of perfect positive relationship. Okay, so R squared is sometimes called the coefficient of determination. And it tells you the percent of variability in your response variable that's explained by the explanatory variable. and it's between 0 and 1 because 0 would mean 0% explained and 1 would mean 100% explained. That's it. See you guys in class.